Okay, so it's Objective 2 of Section 2.2 about parent functions and transformations, Barnett's finite math. The second objective is that the student will be able to transform functions, the parent functions learned in Objective 1, using vertical and horizontal shifts. And so vertical shift goes this way. The graph of y equals f of x plus k can be obtained from the graph of y equals f of x. That's what they give you in the problem, y equals f of x, by vertically translating or shifting the graph of the latter upward k units for k positive and downward absolute k units for k negative. There are a lot of words for translating, shifting, sliding, gliding, using a rigid motion. But you get the idea, hopefully, with all of those words. So let's do this problem here. Graph y equals f of x, the absolute value parent function. That always comes first, right? The parent is always the first one. And then y equals absolute x, and then we'll add 4 on the end. And so the parent, 5. Of course, there's the black one right there. Those three graphs. The familiar V-shaped graph, y equals absolute x. And you can see how, with the addition of a constant 4, well, that adds 4 to all the y values. You can just imagine the table. Instead of -1, -1, it's -1, and then the y coordinate is -1 plus 4. And so -1, 3, I'm sorry, +1, because we take the absolute value. So the point -1, 4 is on that, 5 is on that graph, -1, 5. 0, 0 is on the graph of the parent. 0, 4 is on the graph of the shifted version. And 1, 5, oops, One 5 is going to be on the graph of the shifted version. And from there, you get the idea. So the point is that 4 is added to all the y coordinates, which has the effect of raising the entire graph 4 units. Similarly, downward 5 units for horizontal shift, the third one. Now we've got a constant h thrown in there on the inside of the parentheses, not on the outside of the parentheses. And the graph of the shifted one, horizontally shifted, y equals f of x plus h, can be obtained from the graph of y equals f of x by horizontally translating, or shifting, or sliding, or gliding, or moving rigidly the graph of the parent, h units to the left for h positive, and absolute h units to the right for h negative. So whatever the sign is here, you go the opposite direction. So if it's plus, you go to the left, And if it's minus, you go to the right. Example, graph the parent function, graph the replacement of x with x plus 4, absolute value of, and replacement of x with x minus 5, absolute value of, and if the rule above holds, this ought to be a left shift, the opposite direction of what you might think it should be, and then over here a right shift. And that's what we have. So, and why is that? Well, what you need here are really big values of x to do the same work as what not so big values of x used to be able to do. Okay, so now it takes a big number like 10 to give you an output of 5, absolute 5, which is 5. Output of 5, it takes a 10 to produce an output of 5, whereas it used to be that it took a not so big value of x, just regular 5, to give you an output of 5. And so that's why the graph goes the opposite direction of what you would think under this transformation. It takes big values to get the job done now. So right shift for the minus, and similarly or correspondingly left shift for the plus. We could do two of them, right? What if the problem were graph y equals absolute x plus 4 minus 5? Well, it's an absolute value, so of course we're going to start with graph of the parent function, y equals absolute x, the familiar V-shaped graph, vertex at the origin, and that's stage 1. Then we're going to replace x with x plus 4. We're going to do that graph that we've already seen, y equals absolute x plus 4. And that, of course, is going to mean a shift 1, 2, 3, 4 units to the left. And next stage will be the subtract 5. And that always, no matter what kind of function we're talking about, has the same effect. Y equals absolute x plus 4 minus 5 has the effect of lowering the graph 5 units. So we're going to go down 1, 2, 3, 4, 5. Every point on the graph moves along with, wherever we want to start this. And we end up with this kind of graph. And so in this form of graphing, we actually don't have to plot points. We just need to account for all of the new pieces that have been thrown on there or in there with the parent function. And that will get it done for objective 2.